Why does NumPy's random function seemingly display a pattern in its generated values? I was playing around with NumPy and Pillow, and came across an interesting result that apparently showcases a pattern in NumPy, random.random, results. Here a sample of the full code for generating and saving 100 of these images, with seed 0, the above are the first 4 images generated by this code. The above are 4 different images created using pi.image.fromArray on 4 different NumPy arrays, created using NumPy.random.random 256, 256, 3, 255, to generate a 256 by 256 grid of RGB values in 4 different Python instances. The same thing also happens in the same instance. I noticed that this only happens, in my limited testing, when the width and height of the image is a power of 2. I am not sure how to interpret that. Although it may be hard to see due to browser anti-aliasing, you can download the images and view them in image viewers with no anti-aliasing. There are clear purple-brown columns of pixels every 8th column starting from the 3rd column of every image. To make sure, I tested this on 100 different images and they all followed this pattern. What is going on here? I am guessing that patterns like this are the reason that people always say to use cryptographically secure random number generators when true randomness is required. But is there a concrete explanation behind why this is happening in particular?
Don't blame NumPy, blame PAL, Pillow. Smile, you're generating floats, but PAL expects integers, and its float-to-int conversion is not doing what we want. Further research is required to determine exactly what PAL is doing. In the meantime, you can get rid of those lines by explicitly converting your values to unsigned 8-bit integers. As Knight Mitchell notes in the comments, a more efficient form is. Here's typical output from that modified code. The PAL image.fromArray function has a known bug, as described here. The behavior you're seeing is probably related to that bug, but I guess it could be an independent one. Smile? For you, here are some tests and workarounds I did on the bug mentioned on the linked question.
I'm pretty sure the problem is to do with the dtype, but not for the reasons you think. Here is one with np.random.randint0, 256, 1, 256, 256, 3, dtype equals np.uint32. Note the dtype is not np.uint8. Can you see the pattern? PIL interprets 32-bit, 4-byte, values, probably as 4 pixels RGBK, differently from 8-bit values, RGB for 1 pixel. CPM2 rings answer. Originally you were passing 64-bit float values. These are going to also are interpreted differently, and probably incorrectly from how you intended.
As others have noted, these patterns have nothing to do with NumPy's random number generation. The problem is simply that PIL's RGB mode expects to get an array of dtype uint8, and when given something else, tries to interpret the raw bytes as if they were an array of uint8s. Here, you are passing 8-byte float 64s, NumPy's default when you don't specify a dtype, and this produces the result you see. You're expecting every random number from 0 to 255 in your array to define the value for one color channel of 1 pixel, but in reality, it's defining the value for 8 successive color channels. For instance, the very first random number, which you intend to be the value of the red channel of the top left pixel, is in fact defining the red, green, and blue channels of the top left pixel and the one to the right of that and the red and green channels of the pixel to the right of that. Oops! The simplest test that shows that these patterns are not in fact emerging from NumPy's RNG is to simply set all the values in the array to 255 instead of random numbers, and then display that. Sure enough, we still see a pattern of vertical lines.
The Python docs for randoms say this. Python uses the Mersenne twister as the core generator. It produces 53-bit precision floats and has a period of 219,937 to 1. The underlying implementation in C is both fast and thread-safe. The Mersenne twister is one of the most extensively tested random number generators in existence. However, being completely deterministic, it is not suitable for all purposes, and is completely unsuitable for cryptographic purposes. The best random number generators pass randomness tests. Lesser quality random number generators are often used because they are quick and deemed good enough. In some difficult-to-pass tests of randomness January 2002, by Marsalia and Sang, they determined that a subset of the die-hard battery of tests could be used to assess the randomness of a series of numbers, specifically the GCD, gorilla and birthday spacings tests. See die-harder test descriptions for a discussion of entropy and comments on those tests. Over at our Programming Puzzles and Golf Code, some people took a shot at developing code to pass the die-hard tests in this question: build a random number generator that passes the die-hard tests. You should expect to see patterns in all but the best, and likely slower, RNGs. The modern standard for statistical testing of RNGs, NIST SB 800-22, Recommendation for Random Number Generation Using Deterministic Random Bit Generators, Overview, provides a series of tests which amongst other things assesses the closeness of the fraction of ones to half, that is, the number of ones and zeros in a sequence should be about the same. An article published on the ACM website Algorithm 970, Optimizing the NIST Statistical Test Suite and the Berlekamp, Massey algorithm January 2017, by Sis, Rihar, and Matthias, promises an enormous speed-up of the NIST algorithms with their reimplantation.